So if we look at the complete LO generation block, we'll find that there will be a PLL, which is putting the VCO in a negative feedback loop. So this entire block is the frequency synthesizer, and this output is going to be buffered by multiple stages, and finally we get FLO, which has a nominal value same as the FVCO, but because of this extra circuitry around the VCO along with this LO buffer, the phase noise in the LO signal which will be fed to the mixer will be very different than the phase noise which is present in a free running VCO. So LO buffer output is used to drive mixer in a transceiver. Now if we look at the phase noise of this LO buffer output, which is what we are actually interested in, because the phase noise of this LO buffer output is going to actually decide how much will be the reciprocal mixing, how much will be the degradation in the EVM of the in-band signal. So let us qualitatively look at how the phase noise will look like at the output of LO buffer. Let's say this is the phase noise at the output of LO buffer. For comparison, if we plot the phase noise of the free running VCO, it will have this kind of profile, phase noise of free running VCO. But because of this phase lock loop, we'll find that the phase noise within the bandwidth of this loop is going to be suppressed, and it will mainly be decided by the phase noise of the reference frequency. So we will see that within the bandwidth of the PLL, phase noise is going to reduce, and once the frequency offset is beyond the bandwidth of the loop, then it will mostly follow the phase noise of the free running VCO. But again, at a much wider frequency offset, we'll find that the thermal noise of the LO buffer will start coming into picture, because the LO buffer noise is going to be flat with frequency offset, whereas the phase noise of VCO is reducing with a 20 dB per decade kind of roll off. So at very far offset, you'll find that the phase noise is going to become flat because of the buffer. So this PN reduction within PLL loop bandwidth. In addition, we have got this flat phase noise due to LO buffer. So we should always keep in mind this kind of profile for the phase noise of the LO signal being fed to the transceiver when we are doing any kind of frequency planning, because this is the phase noise which is going to actually affect the transceiver performance. The phase noise of free running VCO indirectly decides the LO phase noise, but the final phase noise is going to be decided by this PLL as well as the buffer which is involved. You can see that LO phase noise is reduced within PLL loop bandwidth and at far offset LO buffer noise decides LO phase noise. As discussed in the transceiver architectures, we need quadrature mixers. And to drive those quadrature mixers, we also need quadrature LO. So far, whatever we have seen that we can generate a differential LO signal, but it is not having that quadrature phase. So now we are going to look at how to generate this quadrature LO signal. So there are multiple approaches to generate this. So let us take a look at the quadrature LO waveforms to the VCO output with the help of quadrature generation technique. Can result in VLO I and VLO Q. If we look at their waveforms, then the phase LO may look like a square wave going between supply and ground, like this, and the quadrature LO will be the same as the in phase LO but with 90-degree phase shift. And the two waveforms are going to have a delay which corresponds to 90-degree phase difference at the LO frequency, which requires delay of TLO by 4. So VLOQ is VLOI, which is delayed by TLO by 4. So from this basic understanding, it looks like as if you can take the in-phase LO signal and add a delay of TLO by 4, and we should be able to obtain this quadrature LO. So we can take this VCO output, let's call it VLOI, add a delay equal to TLO by 4, and then we have got VLOQ. This is your in-phase LO, this is the quadrature phase LO. Now the problem with such a simple realization of quadrature LO generation is that this delay which we are expecting it to be exactly equal to TLO by 4 may not be true in a practical situation, because the delay is going to be again dependent on the process voltage and temperature variations, and under those variations it is difficult to maintain the delay to be exactly equal to TLO by 4. Difficult to create an exact TLO by 4 delay due to process voltage temperature variations. And this results in quadrature error. In addition to that, every time we are going to change the frequency of the VCO, this TLO by 4 also needs to change in the same manner. So for this reason, such a simple strategy for quadrature LO generation is not used. Let us take a look at more popular approaches for quadrature LO generation. Quadrature LO generation techniques. So one way to generate quadrature LO is by using a quadrature VCO. So quadrature VCO has two VCOs which are coupled together, and they're coupled in such a manner that the phase of the two VCOs are always 90-degree phase shifted with respect to each other. So such a quadrature VCO, you will find that also takes more area because now we need two LC tanks, but it can generate quadrature LO signals in the entire tuning range of the VCO. So here, two VCOs are coupled with 90-degree phase shift between their outputs. Another approach is using polyphase filters. So in this approach, an RC based filter is used, and it can take the LO signal input, and this filter can generate signals which are 90-degree phase shifted with respect to each other, and those outputs can be used as quadrature LO signals. Based phase shifting filter. And there is another very popular technique, especially at this few gigahertz frequencies, that is by using divide by 2 circuit. So this divide by 2 circuit requires the input LO to be generated at twice the LO frequency, and then with the help of the divider circuit, we can obtain the quadrature as well as in-phase phase of the divided signal, and those divider outputs are used as the quadrature LO signals. It requires dividing 2 FLO signal, and good thing is this divider circuits can be much simpler to design, especially at few gigahertz frequency in the CMOS process. But the downside is it requires a 2 FLO signal. So at millimeter wave frequencies, the quadrature VCO technique or polyphase filter technique is more popular. But when we are talking about only few gigahertz frequency range, then it is very common to see approach where we generated twice the LO frequency signal with the help of the frequency synthesizer, and then divided by 2 to generate the quadrature LO. It's below 10 gigahertz. So we are also going to look into the details of this divide by 2 approach to generate the quadrature signal. So let us explore this quadrature generation using divide by 2. So if we look at the 2 FLO waveform, then we will see that 2 FLO signal is going to have a period of TLO by 2, where TLO corresponds to the time period of FLO. So we will be having signal like this. The idea is that if we have a 2FLO signal, then we get this rising or falling edges which are 90 degrees shifted from the LO signal, rising or falling edge. So by taking advantage of these extra phases which are available, so now we can use some digital technique to realize a circuit which will have LO signal which is also delayed by this TLO by 4. So if we take this 2FLO signal and design a divider, so that simplest divider can be just a D flip-flop which is triggered by the 2FLO signal, and we can connect the Q bar to the D. So the output of this divider will have frequency of FLO. We're taking this Q bar as another output. We also have the VLO bar. But this is not sufficient to obtain the quadrature signal. To obtain the quadrature signal, we can realize this flip-flop with the help of a master-slave approach, because in a master-slave approach, we have circuit which are triggered by the positive half, and then we have circuit which is triggered by the negative half of the input clock signal. So now we can see that there is a possibility that we can find out when this transition happens in the 2FLO signal, and based on corresponding to that, we can generate a output which will be 90 degree phase shifted. So the circuit which can realize this flip-flop using master-slave architecture will have two D latches. Let's say this D latch has an input D bar in addition to the D. Then we know that the master latch going to require a clock signal, whereas a slave latch will be requiring a clock bar. This output Q will go to T, Q bar will go to T bar. Since we want to realize a divide by 2 functionality, so this Q bar will go to T and this Q will go to T bar. So the circuit in this box is a master-slave implementation of D flip-flop. Using D latches. And this entire circuit is your divide by 2 using D latches. So now we need this clock and clock bar. We need this 2FLO VCO, which can generate this clock and clock bar signal. This is operating at 2FLO. Now, if we look at the timing diagram of various voltages properly, then we'll find that we can take these two outputs as VLOI, VLOI bar, and these two outputs as VLOQ and VLOQ bar. So here these D latches can be generated using various approaches. One simplest approach is using only the static CMOS logic, where we can have this PMOS in a cross-coupled manner to hold the output value, and use the NMOS to set the output voltage based on the input. So this can be, let's say, D and D bar. Here we can get Q bar and Q. And to make sure this latch is clock sensitive, we can add a clock signal at the tail. So this D latch circuit gives us differential input as well as differential output, which is required to obtain all the phases of the LO which are used to drive the mixer.